Okay, welcome everyone to a new edition, session, chapter of field development. The plan I have for today is that you will work a bit on the first exercise of problem of exercise set number 3, just to practice, okay? Because we have discussed quite a lot of concepts, and I'm not sure you said yes, you understand, but I think we need some exercise to make it solid, okay? To make sure that you're understanding. But just before, so today the plan is we will go through problem 1, and that's something that you're going to work in groups. On problem 1 of exercise set number 3, that is due for publication by next Monday. And that's supposed to practice production scheduling using flow equilibrium. Then the second part of the class, we are going to have a short discussion on networks. How do we solve equilibrium with networks? So that's the menu. Then network solving, or also what we call flow equilibrium in networks. And then if we have time, I'm not sure if we will have time, we will do problem, I think it's number 2. Working groups again in problem number 2 in exercise 3. That is about networks. Okay, and I will print it later and we are going to discuss it here. Again, using using flow equilibrium. Okay, any questions? No? So just, okay, one more thing is that the discussion that we have been, during the last classes, maybe the 4 last classes, it's in page 150 of the compendium. So these are some notes I made, and they have on the field performance exactly describing the process that we make, that we have a material balance, then we go to a production model, and then we go back to the material balance. Okay, what happens when we have reservoir simulator? We don't have in this course, but what is the procedure, the potential, what is the potential indicating, and you have exactly the same deduction I made in last class. Yeah, some more comments about potential. Here is the analytical solution I told you last class. If you remember, if you have 2 fields or 2 wells that they have a different, or each one has its own production potential curve, then you try to make that the plateau is the same for both of them, and then you get a second order polynomial that you solve using the quadratic expression. And then you have that article, which is quite interesting, but then you have the flow equilibrium part, that that exactly the available curve, the required curve, the intersection between them, what is the effect of the choke, why in multi-phase flow you have that that strange shape. Yep, and then some comments that we didn't discuss. What happens when you have choke? How is the operational map of a choke? How is the operational map of a pump, that we are going to discuss later? And then we go for networks, okay? So if you want, you can also complement the discussion we are having here just by reading these pages. Yes, so let's, okay, how many of us? Okay, we have 15, so we want groups of 3, so we divide by 5, right? So 1, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So all the number ones are in one group, number twos in another group, number three. Do you remember your number? Yeah? No? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay? So those all number one are going to be one thing. Okay, so it's flow equilibrium in production networks. Okay, as I mentioned before, we can make a network very simple, just two wells commingling to the same place, and the wells are not identical. Okay, in that case, we could make the approximation that we are going to work with one well just because all the wells were the same. In this case, wells are not identical, are different, are producing differently. Okay, so I'm going to ask you now, how do we find the flow equilibrium? We have, let's say we have some chokes here, okay, but they are fully open. Okay, let's say that they are fully open chokes. How do we find the equilibrium point or the rate that the field or that these two wells will produce, the Q total? Okay, so now I will say, divide and conquer. Okay, let's take that system and let's put it in pieces. Okay, let's first look at that branch. Okay, what do we have here in this system? We have one pressure, upstream pressure, and we have one pressure that I call junction, right? But I have is like a co-current system, right? I have a pressure upstream and then I want to calculate how much is the pressure downstream, right? So this will have an available pressure curve, P junction, seen from well 1, okay, that we'll call well 1, and that will be well 2, okay, versus Q, that will be Q of the well 1, right? How that function is going to look like? If it's co-current, if it's available, remember, what is the shape? There are only two shapes, one like this, one like that. How is it going to look like? Like that, okay, going down. Right? And how do we calculate? Assume a rate, reservoir pressure go to bottom hole pressure go to wellhead pressure go to junction pressure. Okay, formation equation, tubing equation, and flow line equation. Right? Now we can do the same with the other well. Exactly the same. Okay, and we will obtain a curve very similar, depends on the characteristics of the well. Okay, let's say that the two wells, they are exactly the same. The tubing is the same, the flow line is the same, but that well has a much higher C2 is much higher than C1, right? How the curves are going to look like if I compare them? Okay, one will be maybe like this, that will be for well 2, and well 1 will be much smaller because this is making this well very powerful. Okay, so that will be pressure at the junction seen from well 2, okay, from well 2, so here should be well 2, and then I look at that system here, and that system is what? I have a pressure, constant pressure at the downstream, P separator, and I have P junction has seen from the flow line, or from the, we usually call it pipeline, okay? And the required pressure, so that's available. This one is available. And this one is the required pressure. And how is it going to look like? Here we have Q total, okay, and P junction as seen from the pipeline. How is it going to look like? Going up. Yep. Now I will say, so how do I find what is the rate of Q1, Q2, and the Q total? Okay, I'm going to propose a procedure. There might be different variations, but the procedure is I'm going to assume a unique junction pressure. Okay, the pressure at the junction has to be the same. It's exactly the same point. A unique junction pressure. Okay, let's call it PJ star. Okay. Then I from available pressure curve of well 1, calculate QW1. Okay, so from that curve I take it, okay, and I say I assume that pressure, come here, okay, that will be PJ star, and then I read QW1 star, right? Then I do the same for well 2. Of well 2, calculate QW2. Okay, so I go and take that curve again for well 2. Then I calculate again the same thing. I have PJ star, go and read here QW2 star. Yes? And then I, from the required pipeline pressure, from the required pressure curve of the pipeline, calculate Q total. And again I have PJ seen from the pipeline, and it does something like that. Q total. So I go with my PJ star down and I read Q total star. Okay, but then what has to be true? Okay, mass conservation in the junction. Okay, that Q well 1 star plus Q well 2 star has to be equal to Q total, right? So then verify, the next step is to verify mass conservation in the junction. Okay, so is Q total star equal to Q well 1 star plus Q well 2 star? No. What do I do again? Repeat, okay, and I assume another PJ, another pressure at the junction. No? If yes, I'm lucky, then PJ star and QW1 star and QW2 star and Q total star is the equilibrium, or are the equilibrium conditions. Yeah, that clear? Yes. Yes.
And what will be the basis of assumption of the junction stuff?
The initial assumption?
Yeah.
Well, you can assume, for example, that that pressure is higher than that pressure, right? And that that pressure is also lower than reservoir pressure. Okay. But you will see that's graphically, and sometimes in the exam we ask you to make it, I ask you to make it graphically, but also you can do it numerically. the equilibrium point is often calculated numerically. Okay, and remember, we have to count the equations that we have and the number of unknowns, right? So we have let's go. So we have IPR equation for well 1, IPR equation for well 2, and how many unknowns we have here? We have Q well 1, right? We have Q of well 2. So let's make it kind of a table. Okay, let's make it okay, because when you have too many things, when you have too many elements in your network, it becomes difficult to do it graphically. Okay, you all the time have to apply mass conservation in the junction, but what happens if you have many junctions? Then it becomes tricky to do it graphically. Okay, then we have to do it just numerically. Okay, so that will be equations. Okay, that will be unknowns, and that will be number of equations that I have so far and number of unknowns. The unknowns, I also have PWF1 and PWF2, right? So I have so far I have 2 equations for unknowns, right? So I continue further. I have the tubing equation, and the tubing equation has this tubing P2, and so let's put it tubing equation 1 and tubing equation 2, and here we have the same unknowns, but we have additionally PWH1 and PWH2, right? So we have, how many unknowns we have? 6, right? But then we have 4 equations. Looks like we are hopeless. We are not making any progress, right? And now we have the flow line of 1 and the flow line of 2, and how many new unknowns we have? We have just P junction, right? So we have 7 unknowns and 2 equations, and 6 equations, right? So far. Then now we have the pipeline equation. Okay, that the pipeline equation has Q total, right? And PJ, that we already had it. So now we have 8 unknowns and 7 equations. And lastly, what is the equation that we are missing? Mass conservation in the junction that means Q total equal to Q1 plus Q2. Then I'm adding no more unknowns, 8 and 8. Okay, I can solve the system of equations. Okay, and that I do, I think here I have a, okay, let's see, we had some nice figure about a lady that is going to help us to solve, that I think you have seen last class. Okay, the lady that helped if we want to solve graphically a network. Okay, we have only 2 available and require cross, but she can do, you know, quite a few. She can have more branches, this lady, but usually we do it. So let's put it here. Okay, Lakshmi. We say graphically is more difficult with increasing number of junctions. Okay. Now, there are, like you saw here, there are two ways that we can calculate, just like in just a single well system. Okay. One, if you remember, one way was to say I find just the equilibrium point, right? And the other way was I force the rate and then I verify that my equipment is operating, how my equipment is operating. So here we can also use the fixed rate calculation method for networks. Okay. If I know exactly in the same case as we had before, okay, the same example, okay, because that's exactly what we have been doing now in this block 2 exercise, okay, that we are fixing the rate and then verifying just that the delta P is greater than 0, okay. If not, we have to solve the network, but first we assume and verify. We can do exactly the same with the network. So let's copy that example again. Okay, and now now we have that choke here. Okay, we're going to take them. That's the element that we are going to take away. Okay, the choke. We're going just to take it to a side, and that will be where I'm going to make my equilibrium point, just in the case of Snowbite. Okay, so I fix desired rates are Q well 1 star and Q well 2 star. Those are my desired rates. So that's my point. So I have to know co-current all the way to that point and counter current all the way to that point. So I say, using IPR and QW star, calculate PWF1 and PWF2, right? I move, but I now have to carry more cells, okay, more columns. In your case, you had only one, and now I have to carry for both wells. Now, using tubing equation, PWF and QW, calculate P wellhead 1 and P wellhead 2, right? And I stop. That's where my equilibrium point stops, exactly here. Now I'm standing in that point. Now I go counter current all the way to that point. Okay, so using pipeline equation, okay, P sep and the total rate, what is it? Q total is equal to Q well 1, right? Plus Q well 2. I calculate P at the junction. Yes, I'm calculating from here to here, from that point. And from that point, I also move back to the wellhead, okay? To the downstream of the choke, using flow line equations for each well. P junction and Q well 1 and Q well 2, calculate, and we're going to call it P downstream of the choke 1 and P downstream of the choke 2. DC is downstream of the choke. And now what do I have to verify if I can produce my rate or not? Okay, I have to verify. The last step is to verify if PWH1 is greater than P discharge of the choke 1 and PWH2 is greater than P discharge 2. It's exactly the same that we have done now. Okay, the only thing now I have to do 2 points. In 2 points I have to make my equilibrium. But everything makes it easy that I fix the rates. I provide the rates in advance. Q will 2 and Q will 1. Okay. So that's a simplified way. If you already have the rate, you can just substitute it in the network and can calculate if your rate is feasible or not. Okay. So let's kind of, if you understood that, okay, these two discussions, equilibrium, and then you have also fixed rate. So let's go a bit higher in level and see a network can be considered as a system of equations on that is only if I have adjustable elements. Okay, if there are adjustable elements, a network can be considered as a function, okay, not a system of equation, but as a function that provides well rates with, that's the output, okay, that's the output of the function, okay, with certain setting of the adjustable elements, okay, certain setting of the adjustable okay, and that's the input. Okay, that means if I say choke opening, okay, I have 2 wells in my system, choke opening 1 and choke opening 2, then I can calculate what will be the rate of each well. Okay, if I have 2 pumps rotating, I give the rotational speed of pump 1, rotational speed of pump 2, and I can calculate how much. So you can see like a function. I think that we have a nice picture in the compendium. Okay, like that. Yeah, of course you need some more things like the properties, you need the dimensions, you need the IPRs, you need many things. Okay, but you can assume that it's almost like a function. Mathematically it's like a function. Okay, and you have, it depends on, it could be smaller. Okay, depends on many things, the IPRs, depending on the dimensions, depends on the all of these equations, but also depends on the adjustable variables. Okay, and depending on these numbers, I will have different solutions. Okay, so just to give you an example, for the 2 well case, for the 2 well case, well system with wellhead chokes, okay, so let's have, we are about to finish, so don't be stressed. So we have that, okay, and we have our separator. Okay, it is possible that I will paint Q1, Q well 1, and Q well 2. Okay, and I will create a region where if I, for example, leave the two chokes fully open, okay, I will find just this point. The two wells are producing, and I will find Q1 and Q well 2. Okay? Now I start choking. So let's see how the area, just to give you a realistic area. Okay. Yeah, better we start like that. So we have the two of them fully open, two chokes, choke 1 and choke 2 fully open. Okay. Now I close completely choke 1, okay, and then I obtain that point. Choke 1 completely closed and choke 2 completely open, right? I won't be producing anything from 1, but I will produce fully from 2, and I can do the same here. Okay, here will be choke 1 completely open and choke 2 completely closed, right? But then if you do any case in between, okay, for example, you leave that one open, okay, and you start opening the other one gradually, open and open and open and open, you will see that you generate a region of rates. All of those rates, okay, if I run my network with infinite choke openings, or with infinite combinations of choke openings, okay, I will get the following: Q1, Q2, okay, we'll get these 3 points initially, 1, 2, and 3, okay, and I will get a region, okay. All of that region, everything that is inside the region, I call it, these are rate combinations feasible to produce, okay. All that is inside, if I want exactly that combination of rates, I will be able to find it by some way of choking. I don't know what, but I will be able to find, for example, choking 80% one and 60% the other. I will be able. But everything that is outside, these are non-feasible rate combinations. Okay? If I want, for example, that combination, you cannot. Okay? No matter what you do, how you choke, etc., you will not find that particular combination of Q1 and Q2. If you are here inside of that region, fine. You can find exactly what combination. You can find a choke combination that you will. That clear? Yeah. Now that's just to also to discuss, okay, the issue that in commercial software, the process of finding the settings of adjustable elements that give a certain rate combination, okay, in our case QW1 star and QW2 star, okay, is wrongly called optimization. Okay, so just be careful. For example, you want that particular combination and you're trying different openings with some numerical method. Okay, you have Newton-Raphson something, to try to drive exactly those rates to the values that you want. Okay, so for example, if we have our function, okay, our network model that depends on the opening, let's call it opening of choke 1 and opening of choke 2, depends on those two parameters. And actually we should put them outside, right? Because that's the input. Opening of choke 1 and opening of choke 2. Opening of choke OC, okay? And we will obtain Q well 1 and Q well 2, okay? When these two are 0, that means I'm fully open, find the equilibrium rate. When this one is 20%, I find a different value, okay? So what I put on top of it is a solver that checks, okay, I have desired values, okay, of Q well 1, okay, let's call it, okay, again star, Q well 2, star, that's an error, okay, a difference between those two values that goes inside a Newton-Raphson, and the Newton-Raphson change the inputs, okay. So what you're trying to make with this solver is saying, I try to find that number, initially, for example, say open choke, find the rates, do they deviate for what I want? Yeah, they deviate. Now I find another opening, substitute, find the rates, do they deviate, and repeat until certain tolerance is matched, okay? And here I have is error less greater than the tolerance, and is error smaller than the tolerance. Okay, so here I have my final solution. Okay, but yeah, just to make you aware, so in the network we're going to have one example, but we're going to make this equilibrium calculation. Okay, we're going to do it in Excel. We're not going to use the curves, we're going to use the equations. Okay, but we're going to see how do you find it, and then we will find another example where you fix the rate and try to find the delta P. Okay, but when we go to GAP, for example, to commercial tools, you will see this way of thinking about network is very useful. Okay, and also be aware that they call optimization to this process to find exactly these settings that give you a particular set of rates. Okay, be aware of that. It's wrongly called optimization, but that's what is done. Now I'm asking you, what happens if you give to the program that you want to find this point? Is that process going to converge? No. Okay. And you get frustrated, you get the tool, you get GAP, don't understand, call technical support, please tell me why. You were really trying to get a rate that is not physically possible to get. Okay? So that process that you have here will never converge because you will never have a combination that will give you that particular rate that you want. Okay? Then what is the problem? You can make that map for simple cases. When you have 3, 4, 5 dimensions, 20 wells in a system, what happens? It's a mess, okay? You have to think, I'm not sure, you have to go to the matrix or something. So it's not so simple to know if your point will be feasible, unfeasible, or feasible. Okay? But if this process fails, there is a very good chance that that particular combination that you wanted is unfeasible. Yeah? Any question? No? So next class we will try to make an exercise also from the exercise set 3 on networks, and we will try to cover that equilibrium and also fixed rate, and yeah, and that's all I think. Then we move on to the next topic. Okay, any questions? No? Okay, have a nice day.